Hello and welcome to lecture 23 of chapter 19. Currently we are doing various statistical tests for hypothesis testing, and we have done one sample t-test and two independent sample t-test. Now this is paired sample t-test. Here also there are two samples, but those two samples are related with each other. For example, suppose there is a company which has launched a training program for its employees. So look, there are two kind of ways by which I can decide whether the training program is effective or not. I can divide my employees into two parts. Say one group of 100 employees will not undergo training, and another group of 100 employees will undergo training, and then I will find their productivity. But in that case, the two 100 samples which I have taken, they are two totally different employees. So that would become independent sample, and there what you will use is this two sample t-test which we have discussed in previous lecture, right? But I can study the effectiveness of my training program in another manner also. This time I don't divide my employees into two samples and some are subjected to training and some are not subjected to training. Instead, I take one sample from my employee and I measure their productivity before training, and then I take the same sample, same employees are then allowed to pass through the training program, and then I measure the productivity of same employees who are trained now. Okay, so then also I can decide whether the training program is effective in increasing the productivity or not, right? So company is launching training program for employees and you measure their productivity before and after the program, right? Now here, what is the null hypothesis? Null hypothesis is always status quo, nothing, no change occurs. So that means the average productivity of 100 employees say before the training and average productivity after the training, both are equal, or that means there is no improvement in productivity because of the training program. Okay, but the alternative hypothesis says that average productivity of the same employees increased compared to when they were untrained. Their average productivity increased or greater, it became greater after they were trained, right? So there is a significant improvement. Now this kind of tests are done because companies often employ this kind of corporate trainers, and these corporate trainers or consultants who are there to suggest certain means for improving the productivity. They are also having costly fees. So before you give a contract for all the employees, or suppose you have a large firm with 50,000 employees, then before you give the contract for all the employees, you would like to take a small sample and give them to that corporate trainer that take this sample and you show me that there is some improvement in the productivity of this sample. So these are untrained people at present. You train them and show me that there is improvement in the productivity. So whether improvement is significant or not, based on that you will decide that whether the 50,000 employee contract will be given to that corporate trainer's firm or not, right? So here we take paired t-test. Similarly, there is a fitness program which wants to ascertain if participants successfully lose weight after 6-week program. So participants here also are saying before the 6-week program, their weight is measured, mean weight of course, and after the 6-week program, their mean weight is measured, and null hypothesis always means no change, status quo. So that means that average weight before the program and average weight after the program, they remain the same. But this alternative hypothesis says that the objective is achieved successfully. So that means that average weight after the program is significantly less than average weight before the program, right? So that is my alternative hypothesis. Now how to test whether this null is correct or alternative is correct, for which you will use paired t-test. Again, the first step is very common, that importing the required libraries, and the only library which is different from our usual libraries is this scipy.stats. From that, import t-test _REL, where REL stands for related sample t-test. Okay, so then we import that libraries and then we do the next steps. Okay, so suppose here this is just creating random sample, and this is a synthetic data which we are creating, in which you have taken a sample of 10 employees, and ideally more than 30 would be great for because it is the assumption of central limit theorem, and you know that hypothesis testing is ultimately based on central limit theorem only, right? So more than 30 would have been better, but just for the demo this will do. Now suppose this is the employee productivity rank out of 20. You have decided some productivity measures, that how many leaves the employee takes, then maybe in how many of the task given, what percentage of the task he completes successfully, in how many percentage of the task he overshoots the time allowed, or everything, and based on that you find one ranking of the productivity. So these are 10 employees ranking out of say 20, and similarly these are 10 employees ranking out of 20 after undergoing the training program. So this was before undergoing the training program, and this is after undergoing the training program. And we create a data frame, right? So data frame says that first is employee ID or rank, then 1 to 10, and before training, so this array will become that column, and after training column that will become this array, right? And then you can create the data frame and you can display the data frame, right? You can also add one more column for difference in the productivity. So that difference column will show that productivity after training minus productivity before training, the difference of that, right? And you get one this kind of simple data frame that these are employees, this is their productivity score before training, and this is their productivity score after training. So you can see that at least some improvement is definitely seen, but whether that improvement is statistically significant or not, that you have to decide. Okay, because such visual in way that yes, improvement is seen, and you can't give that thousands of dollars of contract to that corporate trainer, right? You have to check the p-value and you have to do the hypothesis testing, correct? So you will do paired t-test. Now for the paired t-test, what you will do is every t-test gives the two values as the output. One is the t-value or t-statistics, and another is the p-value. Okay, and here this t-test of related samples that has two variables. One is it takes two arguments. One is the productivity before, so that is this array, this, and another is the productivity after, that is this array, right? And then it automatically performs all the t-tests, so we don't even need to bother what is t-test and how to perform t-test and which tables I have to look. Nothing doing. Our program is because Python has so many such functions that it is a statistical powerhouse. Just like R programming language is also favored by statisticians, but Python is much more dynamic because it is not only statistical powerhouse, but it is also powerhouse for machine learning, artificial intelligence, deep learning, and so many other things. So this test, when you supply with these two NumPy arrays will directly give two results, t-statistic and p-value, and we will print those values. So let us print those values. Now here p-value is 0. 0 means it might be so small that 0.00000 something 3 say. So that means this is my significant level, then my p-value is much less than significant level. Okay, it is less than 0.05. So I will enter into this part and I will say that my null hypothesis would be rejected. Now what was my null hypothesis? That average program, no, that was not for productivity, that is a training program, right? So that is the average productivity before the training program and average productivity after the training program remains same, or there is no improvement in the productivity because of the training program. That was my null hypothesis, but here I am not getting that that result. I am saying that null hypothesis must be rejected because my p-value is much less than, in fact it is 0, so it is less than the significant level, right? So therefore alternative hypothesis must be accepted. So I will enter this else part, reject the null hypothesis, or that means, sorry, not else part, I will enter the if part and therefore reject the null hypothesis. So if null hypothesis is to be rejected, so then in that case, alternative hypothesis is correct, or there is a statistically significant improvement in productivity because of training program, right? So I can print that result and I will get that reject the null hypothesis, training program significantly improves the productivity. Here also you can see this thing, that when t-statistic is large, then chances of p-value falling below the significance level are always high. Again, but large and small are very relative number, and therefore that minus sign is okay, but large in magnitude. Okay, so at that time chances of this p-value falling less than alpha, that is this, or that is chances that null hypothesis would be rejected, that are always higher. Okay, however, we never decide based on t-test, but we decide only on the basis of p-value. Okay, so next is we try to verify. Okay, from p-value we found that null hypothesis is to be rejected and the training program improves the productivity significantly. But let us check it by plotting box plot, by plotting a line plot, and by plotting histogram. Okay, so for that, this is a paired line plot. So that will give me a kind of distribution, data distribution, like for example, KD plot we have seen, okay, or normal distribution, and they will be overlapping on each other because one is the before training situation and another is after training situation, and okay, productivity increases, but that will not increase by so much amount that you will get two different data distributions for the same data, because ultimately your data is same, right? So let us plot, and you will see first was the box plot, and you can see a prominent increase in the productivity. The median productivity before training was somewhere 12.5, and the median productivity after training is somewhere in 14.5. Now that 2 units of increase in the productivity, multiply that by, suppose if I apply this training program for all my employees, then the productivity gain for 50,000 employees will be how much? Okay, now then this is I think a paired line plot, right? So that shows again the blue is the dot before productivity and the green is the dot after productivity for various different samples. So I have taken sample 10, 11, 12, 13, 14. There are productivity scores. So that is before productivity, that this kind of scores, right? And after productivity, same scores change in what manner? Then you can either show it by a simple this kind of table that the productivity scores improve, or you can show by more creative manner like this kind of uh, paired line plots like that. Okay, so you can see that productivity definitely improves. Now the third plot is this distribution of productivity differences that is plotted by this histogram of differences along with the distribution. KD is equal to true. So it gives the uh, distribution also. So these are two histograms. One is before the training and another is after the training. And this is the distribution plot. Now it shows that for majority of the employees, the improvement is positive. So that means out of a sample of maybe 100 employees, it might be that productivity of one or two employee actually decreased after undergoing the corporate training. But on an average, or rather than on an average, for majority of the sample, the productivity gain is positive. It is above zero, right? So that is what is shown by the distribution plot. This is the explanation of the visualization which I have already done, right? So in next particular lecture, we will discuss about this ANOVA, analysis of variance. Okay. So here, this was the discussion about paired t-test or related t-test for related samples. And for that, we imported from scipy.stats import t-test related. Now, the only thing which is imaginary in this whole example which I have done is this data. So instead of creating the synthetic data like that, whenever you are working as a data scientist, then the HR department will give you this kind of data. That suppose this is 10 employees, or instead of 10, it may be 100 employee sample. Then these are their productivity ranking. You don't have to bother how that they have decided their ranking. You just have to ask, these are ranking out of what? So these are ranking out of, this is 12 out of 20, 15 out of 20, 14 out of 20, and so on. Okay. So on a scale of 1 to 20, these are the original productivities that the HR department will give you, and these are the new productivities. And so this data will be actually given to you from experimental situation. Rest of the things will remain exactly as we have done, and you will first calculate P statistic. Since P came out to be much less than alpha, 0.05, then you will reject the null hypothesis, and null hypothesis says that there is absolutely no change in the productivity or average productivity of employees before and after the training program was same, but you reject that and you say that no, average productivity after training program is significantly higher than the average productivity before the training program, and therefore you will assign the job of that corporate training to that trainer. After, of course, maybe you want to conduct more tests, other tests, then you can do that. But at least one paired relative t-test that confirms that his corporate training is effective, right? So next lecture we will talk about this ANOVA. So stay tuned. Thank you.